Team, let's talk about the rational method. This is a relatively simple method that we can use to estimate the peak discharge for small drainage basins. And when I say small drainage basins, I'm talking about less than approximately 300 acres. The bigger your watershed gets, the more you have to account for the travel time and routing and flood waves through channels and stuff like that. So to do this, I'll just write the equation out first and we'll explore it. Peak discharge in units of CFS is equal to C, the rational method coefficient, times I, which is the rainfall intensity, times the drainage area. That's the equation. And let's take a look a little bit more at these coefficients. C is kind of like the curve number, except instead of going from 0 to 100, it goes from 0 to 1. And so it's a fraction. And we can kind of think of it as the fraction of runoff. We'll just say volume of runoff all over the volume of our rainfall. That's kind of approximately what it is. And you can look these values up in a table. In the homework, I give you a table to consult. So you could imagine that kind of a more impervious area would have a higher runoff coefficient, maybe something like 0.9 or something like that. This is our rainfall intensity, and it has units of inches per hour. We'll unpack that in a minute. And then this is our drainage area in acres. So I'll note that this equation doesn't look dimensionally homogeneous, meaning this is non-dimensional. Inches per hour times acres does not equal cubic feet per second. But I will note for you that if we do inches per hour, inches per hour times acre, that is equal to about 1.008 CFS. And in the homework, you can do this conversion for yourself for some bonus points. So take a look at that. This coefficient or conversion factor is often left out. This is a big approximation. We don't need to estimate our CFS to the nearest 10 thousandths. So, or hundreds even. So, really we're just kind of getting a ballpark estimate with this equation. And I will note also that this equation has roots back to 1850s in England. So it's pretty old school, but we can use it kind of as a back of the envelope approach. And it's very common, you'll see problems using the rational method on the FE exam. So be ready for that. The thing I want to unpack the most with you guys is this rainfall intensity and where this number comes from and how we estimate it. This rainfall intensity is going to be linked to the duration of the storm event through an intensity duration frequency curve. And we also need in order to kind of estimate this I, we also need to think about our duration. So let's look at the, we'll just say estimating I. Let's look at our rainfall intensity duration curve, intensity duration frequency curve, IDF, where we have intensity, inches per hour. On the y-axis, we have duration, maybe hours on the x-axis. And then we have different curves based on different frequency rainfall events. So maybe this is the 50% AEP, and maybe this is the 10% AEP. We'll have different durations down here. So this could be 1 hour storm, a 2 hour storm, a 6 hour storm, something like that. Now, often the problems are set up, or if you just kind of think about the design problem, you've got a watershed. And so say we kind of know it's some sort of like, urban setting and it's got parking lots in it and parks and whatever, and say it's 100 acres, something like that. So we've got this setting, we know the drainage area, we can estimate the C value from this table. And say I want to understand, I want to design a culvert to accommodate this peak discharge, and you know the CFS for a given frequency event. And so say we'll just pick the 50% AEP. Well, how do I figure out the intensity? Because they could have a range of intensities depending on the duration of the storm. Well, what duration should I pick? And let's think about that. If we go back to our concept of time of concentration, how long does it take for water to travel from the top of this basin all the way to the outlet? That's our time of concentration. And if we pick a duration of the storm event that's for a given frequency that is less than the time of concentration, well, you're not going to get a big peak discharge necessarily. You're not going to meet that maximum. Everything's connected, everything's flowing out. You're still kind of working your way up to the peak of that hydrograph. And that is if your duration is less than your time of concentration. Well, if your duration is more than your time of concentration, you're past that peak, you're at the equilibrium point, and it doesn't really matter. So that's going to be a lower intensity. So we want to hit it just right. So if we pick our duration to equal time of concentration, then we get to that peak, and we are able to have kind of every part of the watershed is contributing to the flow at the outlet. So that's what we'll do. We'll pick the duration equal to the time of concentration. And so for our example, we'll just say, we'll give you the time of concentration, but you might have to calculate the time of concentration on your own. In which case you might run into some problems because the time of concentration has implicitly some rainfall events in here. And so it might be an iterative solution. I'm not going to go into that. We're not going to do that in this class. But if you kind of want to do it properly, there might be an iterative solution involved. So just something to keep in mind. All right, so that is the rational equation. Let's do a quick example. And so for example, this is actually an example in your book on page, well, we'll just do it together. Okay, so for example, we have a 4-acre asphalt parking lot. And we want to design a culvert that can accommodate the peak discharge for the 5-year occurrence interval storm. And we'll note that the 5-year occurrence interval storm is 1/5, which is equal to 0.2% AEP storm, just to keep that in mind. And I'll give you, in this example in the book, it doesn't give you the time of concentration, you have to calculate it, but I will just give it to you. Time of concentration is equal to 10 minutes, pretty fast, right? It's a 4-acre parking lot, and we're going to do overland flow. And then if you look at a table, you know, asphalt parking lots, there's going to be some infiltration maybe somewhere, so we're going to give it a runoff coefficient of 0.95. So how do we calculate this? How do we do this problem? We'll write out our equation first. Q peak is equal to C times I times A. We've got our A is 4 acres. We've got our C is 0.95. We just need to figure out what this I is going to be. So I'm going to do that. I'm going to zoom in. This is a rainfall intensity, duration, frequency curve, an IDF curve. And it is for this area. This example is for Tallahassee. So it's really detailed, and it shows us durations and intensities for just minutes, right? So 10 minutes. Let's see if we can draw on this. We can. So we're going to draw up here. for a 10-minute duration. We're going to equal that to the time of concentration. Remember, TC is equal to duration. And we need to find this 5-year occurrence interval curve, which is right here, this third one. And there's our intersection point. So let's zoom in. And we see that we'll just, you know what, we'll just call it 6.5 inches per hour. All right, so Q peak is equal to 0.95 times 6.5 inches per hour times 4 acres. Let's go ahead and do that calculation. 0.95 times 6.5 times 4. And that's going to give us 24.7 CFS. And we'll note if we did that conversion factor, that 1.008, it's going to give us 24.9 CFS. Yeah, if I'm doing this problem, I'm going to round up to 25 CFS regardless. So we'll just say 25 CFS because, frankly, this is a real big approximation. So that's how we do the rational method, and that's what you'll do for the problem and homework assignment.